Alrighty, guys, welcome back to Calc 1, MAC2311, section 004. Today, we are going to keep talking about the derivative and rates of change, which we introduced last time by saying we're hunting for tangent lines. I'm going to give you an alternate recipe or formula for that slope of the tangent line, aka the derivative. And we'll look at some application problems where we can interpret these things as real-world rates of change to kind of help contextualize the mathematics that we're doing. Other big task for today, of course, is to interpret the derivative as a function, which is a neat thing. The idea that the derivative is not necessarily the slope of the tangent line, which is something that kind of happens one point at a time. But if you think of all of those slopes at once, those are all outputs for something. That something is a new function. So the derivative is really a function in its own right that we can study. It has a graph and all of those things. And we'll see the connections between the graph of the original function and the graph of the derivative. And we'll practice kind of going back and forth from one to the other. So without further ado, let's get into the document camera and do the thing. It's nice to see many of your faces here. And I'd just like to remind everybody that that is something I really appreciate. If you're somewhere you can turn your camera on, if that's a possibility for you, that really does help me just by being able to see your face, just tell how comfortable you are with the material and how the pacing is going. So if you are somewhere you can turn on your camera, I'll ask that you please do that. Help us feel like we're all here together a little bit more. This is MAC2311 section 004, which is Calc 1, and the date today is the 21st of January 2022. Today, we're going to do more tangent line calculations. And we're going to talk about rates of change, which is all section 2.7 stuff. And then we're also going to talk about the derivative as a function, which is section 2.8. So these are our final topics for this week. Maxwell, no sir, Max, come here. Okay. So my wife had to run to the store for a second, which means I'm watching the baby and the puppy at the moment. So I apologize if I'm distracted, but she should be back any second now. Let me just remind you, last time, that the slope of the tangent line to the curve y equals f of x, the graph of that function. Get up. Nice. Cool. Go down. There you go, big boy. The slope of the tangent line to the curve y equals f of x is, I should say, at x equals a is the following expression. F primed of a, this is the notation we use. And what we cooked up last time was that this should be the limit as x approaches a of the ratio f of x minus f of a divided by x minus a, right? And that ratio inside the limit we said was the slope of the secant line. So by taking the slope of the secant line to f of x from x to a and sending x to a, we brought those points close together, which yielded the slope of the tangent line. I'm not going to redraw the whole picture here, but the basic vibe was, if this is a and x was over here, then this point was a comma f of a, and this point was x comma f of x. And we try to get our tangent slope should look something like, slope of the tangent line, something like this, as a limit of slopes of these secant lines. So by taking this point over here and dragging it over here, we're able to pass from the secant line to the tangent line. And it's the limit that does that dragging. And of course, the thing we want is the slope of the purple line, the slope of the tangent line. There are some bits of terminology. I'll take this as a definition, right? We didn't say this last time, so this is the new stuff beginning. We say that f is differentiable. And I know that word is a real mouthful, differentiable or just differentiable. I'll abbreviate this as diffbul at the point x equals a if the limit defining f primed of a, that limit up there, both exists and is finite. All right. So if the limit defining f primed of a, this thing, if this limit exists and the limit comes out to a finite number, right, not positive infinity or negative infinity, if both of those conditions are met, then we call f differentiable. And it's something that happens one point at a time. So a function can be differentiable at 2 or at 3, but not differentiable at 4. Differentiability can be thought of as a smoothness condition, kind of like continuity, right? So a graph is continuous if it's a function is continuous if its graph is connected, and specifically we say continuous like everywhere if the graph is connected everywhere, if at every point that definition of continuity is satisfied. Differentiability is like another step up in smoothness conditions. So if the graph has any jagged points, what we're going to see is that even though the graph may be connected there, i.e. the function may be continuous there, it's possible that the function is not differentiable there. And so when I say smoothness condition, I literally mean smooth. I mean gentle curves rather than hard edges. This definition is extended just a little bit. We say f is differentiable or diffbul on an interval I if, on interval I, if the limit defining f prime of a exists and is finite for all for all of the numbers a living in the interval I. In other words, a function is differentiable on some interval if it's differentiable at every point in that interval. And then the last kind of extension of this, we say f is differentiable full stop, right, with no qualifiers, like not differentiable at a, not differentiable on the interval I, just differentiable period, if it is differentiable at every number a in its domain. right? So differentiability just means the derivative exists, right? The derivative exists, that you can find the slope of the tangent line. I'll show you how it's possible for that to fail. And then just be mindful that differentiability is a smoothness condition, and it is a strictly more intense smoothness condition than continuity. So it is possible to be continuous but not be differentiable. But the turnaround is not true. If you're differentiable, you're automatically continuous. And in fact, that theorem is what I'd like to share with you right away. If f is differentiable at x equals a, then f is continuous at x equals a. So if you're smooth, you're connected, right? If a curve is smooth around some point, then the graph can't have any jumps or holes. You can't be smooth if you are broken. So to illustrate this theorem, I think it's nice to explore the converse. The natural question to ask is, okay, if f being differentiable automatically means it's continuous, is the other direction true? Does being continuous mean you are differentiable? And for a long time, people thought this was true. People thought that continuous and differentiable were the same thing. They thought that every continuous function would have a derivative defined everywhere in its domain. But there are plenty of examples we can look at to show that that's not the case. It just took folks a minute to figure it out. I'll hold here just for a second if people are still writing, and then we will move on. Okay, here we go. So, example, show that f of x equals the absolute value of x is continuous everywhere I should say, and then find the interval or intervals on which f is differentiable, right? And kind of the implication here is that this function is continuous everywhere, but not differentiable everywhere. Now recall that continuous at x equals a means the limit as x approaches a of f of x is equal to f of a. So if I want to show that this function is continuous everywhere, I need to show that this is true for that function at any real number a. That's what I need to show. So we need to show that the limit as x approaches a of the absolute value of x is equal to the absolute value of a for all real numbers a. Because the domain of the absolute value function is all real numbers. This is not terribly hard. We consider three cases. Actually, we could we consider, yeah, 3 cases is going to be a nice way to do it. If a is less than 0, if a is equal to 0, and if a is greater than 0 separately. We could boil it down to 2 if we wanted, but we might as well just do it like this. Right, so this is for the 3 things we need to show for the first part of the problem. We need to show that the function f of x, absolute value of x, is continuous everywhere, which means this limit equation is true for all real numbers a. And I'm going to think about the set of all real numbers as the set of negative numbers, 0, and the set of positive numbers, because the absolute value function behaves a little different on each one of those sets. If a is less than 0, then f of a is the absolute value of a is negative a, because that's what the absolute value function does to negative numbers. It multiplies them by -1 to make them positive, right? Thus, the limit as x approaches a of the absolute value of x is the limit as x approaches a of negative x is negative a, which is equal to f of a, right? If f of a is negative a, and the limit as x approaches a of f of x is also negative a, then yeah, we're good. So that's a big old checkaroonie. If a is equal to 0, then the absolute value of a is, well, that's just f of 0 is the absolute value of 0, which is 0. And the limit as x approaches 0 of f of x is lim x to 0 of absolute value of x. And this is a limit that we looked at before when we talked about continuity, right? You can think about this coming from the graph, right? If you look on the graph of the absolute value function, as you walk in from the left, you're going to 0. As you walk in from the right, you're going to 0. This limit is 0. So f of a is 0, and the limit as x approaches a of f of x is 0. So that's another big checkaroonie. Right, and we could finish it by saying which equals f of a, right, a is 0.
Or the
And then
statement
if a is positive, then the limit as x approaches a of the absolute value of x is, let me come down here, is the limit as x approaches a of x itself, right? Because I'm considering positive values for x, the absolute value function is just x itself. And of course, that is a. And f of a is just the absolute value of a, which is a. So that's also, so that's a third big check. So the absolute value function is indeed continuous everywhere. And you could argue that from the graph if you wanted. It's less rigorous, but you could just say the graph is a single unbroken piece. The only place where you have to think about it at all is at 0. But those 2 pieces do meet up at 0. There is no jump or hole or gap. So
the statement,
this function is continuous everywhere. But what about differentiability? to explore differentiability, we use the limit definition, lim x to a, f of x minus f of a divided by x minus a. Right, this is what should yield f prime of a. And for our function, that would be the limit as x approaches a of the absolute value of x minus the absolute value of a, all divided by x minus a. And again, we consider three different cases. If a is positive, negative, and 0. If a is negative, then the absolute value of a is negative a, right? Let's assume a is negative and try to find f prime of a. F prime of a, according to what we've got written up there, should be the limit as x goes to a of absolute value x minus absolute value a over x minus a. And we're assuming that a is negative. So I'm taking the limit as x approaches a negative number. Well, that means that those x values have to also be negative themselves. Right? I cannot approach -2 with a positive value for x. -2 is all the way on the other side of the y-axis. So all of the x values in this limit, they have to be negative as well. So what that means is that this is lim x to a. The absolute value of x and the absolute value of a would be -a and -x. And downstairs, we still have x minus a. And the reason for this is that a and x are both negative. So we get lim x to a. You can factor a negative out from this. And what's left in there is x minus a. And downstairs here is also x minus a. Cancel schmancel, and you get -1. In other words, if a is negative, then the derivative of the absolute value function is -1. And this shouldn't come as a surprise. If you think about the graph of the absolute value function, the slope on the negative side is always -1. Bump this down so you can see the graph here, right? Everywhere over here, the slope of the tangent line would have to be -1. If you take any point like here and draw the tangent, that tangent is it's gonna be the same as the graph there. The tangent line would just be this line. Okay. I'm going to skip over a equals 0 and jump to a being greater than 0. If a is greater than 0, then f of a is just a, and f primed of a would be, again, limit x goes to a, absolute value of x minus absolute value of a over x minus a, which is limit x goes to a. The absolute value of a is just a because a is positive. Downstairs here, I still have my x minus a. And using the same logic that we used up here, right, I'm taking the limit as x goes to a positive number. So the x's have to be positive as well, which means that their absolute values are positive. So the absolute values just go away because both x and a are positive. And this limit is even easier than the last one. That's the limit as x approaches a of the constant function 1, because x minus a over x minus a is the constant function 1, which is 1. So what we've shown here in the first part is that f of x equals the absolute value of x is differentiable for all negative numbers a, and the derivative there is -1. Here what we've shown is that f of x equals absolute value x is differentiable for all positive numbers a, and that the derivative there is always equal to +1. So f of x equals absolute value of x is diffable on the intervals -infinity to 0 and 0 to infinity. Right? Differentiable for every negative number and differentiable for every positive number. The question is, what about right at 0? Say if a is equal to 0, this is the one where we need to be a little careful. Then f primed of a should be equal to the limit as x goes to a of the absolute value of x minus the absolute value of a over x minus a. And since I'm just talking about one particular value for a here, not like any positive number or any negative number, I can actually plug that bitch in. This is lim x to 0, absolute value of x minus absolute value of 0 over x minus 0. Which is the limit as x goes to 0 of the absolute value of x over x. And that turns out to be an interesting limit. So I'll give you a second to catch up. We've gone through a good chunk of the problem. We're about to get to the kind of heart of the matter, though. So I want to pause, let you catch up, ask any questions.
Can you repeat that what you said about if a equals to 0?
Robbie, I can't quite hear you. Are you asking a question? I see you talking, but I can't hear you. Make sure it's my volume up.
Stunt jumps all over the place.
Oh, I see. I've got YouTube playing in the background. I had my volume down. My bad. All right, let's try that again. What were you saying there, Robbie?
Where it says for that one, if a equals to 0, then f prime of a. How did you get the limit of x goes to 0? Can you repeat that one?
Oh yeah, so I'm just taking that same formula for the derivative of the absolute value function, and then from here to here, I'm just plugging in 0 for a.
Okay.
So I couldn't do that in the previous part because here we're letting a be an arbitrary positive number. So a, rather than being some specific number, was just any positive number in the previous part, and I had to leave a as a. But down here, I'm only concerned with this one particular value for a, which is 0. So I can go ahead and plug it in my formula, which makes life much easier.
Okay.
Any other questions or comments so far on the argument? the crunchy step, if there is a crunchy step, is the blue stuff, right? Being able to get rid of the absolute values in this limit is the trick. And the way we do that is by saying, well, if the inside of the absolute value is negative, then the absolute value of that thing is the negative of that thing. That's the sticky points there. So you might want to think about those for a minute as you review your notes. So we're ready now to take a look at this limit. Obviously, I cannot get here by plugging in 0. And I also cannot cancel because I cannot get rid of the absolute value because I'm not taking a limit as x goes to a positive number or as x goes to a negative number. Here, if we were to look at the one-sided limits, from one side, the x's are negative. From the other side, the x's are positive. So this limit requires looking as x goes to 0 minus and x goes to 0 plus separately. This limit. So the challenge is that the absolute value is kind of a box that's hard to pull apart. If you know that the thing inside the box is negative, you can pull it apart, slap a negative up front. If you know the thing inside the box is positive, you can just lose the absolute values. But here, since I'm taking the limit as x goes to 0, the x values in that limit could be just to the left of 0 or could be just to the right of 0, meaning they could be negative or could be positive. So I can't just ignore or dismantle the absolute values, which means I can't cancel. But when I look at the limit as x goes to 0 from the left of the absolute value of x over x, within the one-sided limit, the x's are all negative because I'm approaching 0 from the left. So this would be the limit as x goes to 0 minus negative x over x. And negative x over x, there I can cancel. No more absolute values. I just get -1. So this is the limit as x approaches 0 from the left of the constant function -1. And the limit of a constant is the constant. So this is -1. And if I look at the limit as x goes to 0 from the right of the absolute value of x over x, here, since my x's are coming into 0 from the right, the absolute value of x is just x because those x's are positive. So this is just the limit as x goes to 0 of x over x. And again, now that the absolute value is out of the picture, I can cancel. And this is the limit as x goes to 0 plus of the constant +1, which is +1. Therefore, the derivative f prime of a does not exist when a is equal to 0 because the limit of here defining it does not exist. The limit which defines it in other words, this function is not differentiable at 0. So the absolute value function is continuous everywhere. That's what we showed in the first part. The absolute value function is differentiable on the negative reals, and it is differentiable on the positive reals, but it is not differentiable right there at 0. In conclusion, f of x equals absolute value x is continuous on the whole real line, negative infinity to infinity, but only differentiable on negative infinity to 0 open, union with 0 to infinity open. So this provides a counterexample to that intuitive idea that if the graph is continuous, then it's automatically differentiable. It's not a true statement. People like to ask me, is this going to be on the test? Right? Is because so little of the homework looks like this, right? So much of the homework is like, find the tangent line, do the calculation, give me the number. Very little of the homework is like, is this function differentiable at this point? I will ask you qualitative questions about differentiability on the test. And I could ask you maximally simple quantitative questions about differentiability. Like, if the derivative has these properties on these intervals, is it automatically true that the derivative has, the same property at this number? Or is it possible for a function to be continuous at x equals 5 and not differentiable at x equals 5? Or I could ask you to sketch a graph of a function that is continuous at some number, but is not differentiable at that number. I've included 1 or 2 homeworks in the current problem set that do ask you to do this sort of thing, and they have optional but built-in tutorials. So you don't need to go through the step-by-step tutorial in WebAssign, but if you're feeling a little bit lost because these arguments do take some time, they're built in there for you. And of course, you can always ask me for help in office hours and stuff like that. So yeah, questions of this nature could show up on the test, but they would be a portion of this argument rather than the whole of the argument. Real quick, before I move away from this, I don't want to spend too much time here. Graphically, and we said this, diffpol means smooth, and continuous means connected. The absolute value function at 0 is connected, but not smooth. Right? It has a hard edge there. And no matter how much you zoom in, you can play with this in Desmos, no matter how much you zoom in on the point here at x equals 0, it will always have that pointy thing. It never gets smooth when you zoom in a lot. Other things that can happen like this include cusps. Again, here you would be connected, but not smooth. And then the final way that differentiability can fail is kind of looking cuspy, but doing something like this. Now this is at appearance connected and smooth, but you have a problem going on here called a vertical tangent. Which means the derivative is momentarily undefined there. So these are how you can be continuous, but not differentiable. All three of these graphs are continuous at the indicated point, but are not differentiable at the indicated point. Okay, these are all ways that the limit defining the derivative can fail to exist. Here, the limits would fail to exist. And here, the limit defining the derivative would fail to be finite. I do want to show you an example of something like this. I don't want to grind too much time on it. In fact, the one from your homework is the cusp form that I've drawn here, just moved over to the left. So I'll do it in Desmos. I'll show you real quick. Oh, ignore that. So absolute value, like I said, no matter how much you zoom in, he's always pointy, right? Never in here do you get to a place where this is like, oh, now it smooths out, so I can talk about the tangent line there. I can't talk about a tangent line there. The other flavor of this, sorry, this sort of thing. Right, this is pointy, it's even pointier, right? The other one is like, is pointy but not sharp, right? The absolute value is like pointy but not super sharp. This one is like pointy and sharp. These are both bad news. These are called cusps, right? And if you look at the tangent line coming in here, it would become vertical. But the slope of the tangent line goes to negative infinity here, goes to positive infinity over here. So just to expose you to these graph shapes where interesting things with the derivative can happen. Before I wander any more into the derivative as a function, I want to look at one problem where we're playing with rates of change. Where is that velocity thing? It's a good velocity problem here somewhere. Velocity. Okay, they do go ahead and define that thing ahead of time, so we'll do that. Well, I'll go ahead and give you the other definition, and then we'll do the velocity problem. So the limit definition we have for the derivative is sometimes called the definition of the derivative at a point. Sometimes it's more convenient. So, sometimes the following limit is better for finding the derivative. And they introduce it with which variable? Yeah, okay, A. F prime of A, same thing, literally the same thing, is the limit as h goes to 0 of, we've seen this, f of a plus h minus f of a all divided by h. The two really do say the same thing. And this is sometimes called the limit of the derivative as a function. versus the limit of the derivative at a point. But I don't make any such distinction. You can use either one in either instance. This is actually a little more common. You'll see this definition a little more, but they do the same thing. The picture that comes with this one, I haven't really been happy with any of these pictures I've drawn yet. So let's try to do this one nicely. Instead of talking about x and a, I can talk about a and a plus h. Again, the idea is to take a limit of slopes of secant lines to get the slope of a tangent line. So if I hold the point at A fixed, and I drag the point at A plus H over here, the blue secant line will turn into the purple tangent line, as we've seen. The difference is just a difference of notation. So instead of calling this like A and calling this X, I identify this point by its distance from A, which I call H. So the horizontal separation there is H. And by sending H to 0, I bring the points together. Same sort of thing. Okay. And you can also say, compare this with the limit we've been using, lim x to a, f of x minus f of a over x minus a. Same exact thing, just slightly different notation. Really quick, while we're here, there will 100% be problems on exam 1 where I say, find the derivative of this function using the limit definition. When I say that, what I mean is either one of these. I don't care which one, but if I say use the limit definition of the derivative to do blah, 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 you need to employ one of these limits. If you solve such a problem without employing one of these limits using tricks you learned in another class or something you see reading ahead or anything like that, then I cannot give you credit for such a problem. Okay, now we're ready. So, some real world stuff. The derivative measures something special. It measures what's called the instantaneous rate of change in the output of the function. So you know that slopes, in particular slopes of secant lines, represent average rates of change. All right? In fact, that's usually how they're introduced in pre-calculus, is by talking about the average rate of change for a function. Well, this derivative, or the slope of the tangent line, represents an instantaneous rate of change. Instead of asking how much is this function changing over some interval, I'm asking how much is it changing right this moment. The easy comparison here comes from physics. If you're driving a car, right, I can talk about my average speed over a trip, but I could also talk about my instantaneous velocity, or my exact speed at any moment during that trip. So like the average rate, of change, this comes from, I'll just put a little tilde here. This comes from secant lines. And this is kind of like your average speed. The instantaneous rate of change is associated with tangent lines and is like your actual moment-to-moment speed. And the tilde here just means like is associated with. Right? So average rate of change is like an average speed. It's like something that you would think of as the slope of a secant line. The instantaneous rate of change is like your actual speed from moment to moment along the trip, and it's associated with a tangent line, or the derivative. And in fact, there are deeper connections. The three classic functions studied related to kinematics are displacement, or position, velocity, which is the rate of change of your position, or the derivative of your position, velocity, speed, but with a sign, and then acceleration, which is the rate of change of your rate of change. It's how your velocity is changing. So if your velocity is increasing, that's a positive acceleration. All right, when you put your foot down on the gas, that doesn't make the car go a certain speed, that makes the speed increase. All right. So the specific examples from physics, I'm going to use the notation your book uses. Some people use S, some people use X. They're going to use S, yeah. In physics, if S, and I'll call it just S of t, is position, then velocity given by the velocity at any moment A is the derivative of your position, S primed of A. So your velocity is the rate of change for your position. How fast is your position changing with respect to time? Well, that's how fast you're moving along the ground. Further, we call the acceleration one C, two L's. I'm terrible at this. We call the shit, I'm embarrassed now. I need to check. Acceleration, they don't even list it here. Oh no, I can't keep hunting. That's even worse. C-C-E-L-E-R-A-T-I-O-N. There might be a double L. We call the acceleration which is the rate of change of velocity A, or A of t. And now this notation is getting quite sloppy because we're using lowercase a for both of these, but that is the standard notation. And A of A is V primed of A, where the little a inside is a specific time. In other words, S primed is V, and V primed is A. So the derivative of your position is your velocity. The derivative of your velocity is your acceleration. All right, let's try to demystify some of this crappy notation and spelling with an example. So is that the first one? Do we have a better one? Okay. So a ball is dropped from the upper observation deck of CN Tower, 450 meters above the ground. We want to find the velocity after 5 seconds, and we want to know how fast is the ball going when it hits the ground. What we would need, of course, is the displacement function, right? So let me parse this in the language that we're using here. What function? 4.9 t squared. A ball is dropped from the top of a 450 meter tower. T seconds later, it has fallen. S of t equals 4.9, right? 4.9 t squared meters. We want to find the speed. Oh, sorry, my document camera just decided to turn itself off. We want to find the speed. I'll just come back over here. Ignore that. Find the velocity at the moment 5 seconds after the thing is dropped. So find the speed 5 seconds after the ball is dropped. And we also want to find how fast the ball is going when it hits the ground. Those are our two tasks. Okay. Ball is dropped from the top of a 450 meter tower. T seconds later, it has fallen this amount, 4.9 t squared meters. Find the speed. Ball is falling. They shouldn't call it velocity in this problem. I'll tell you why later. Is falling at 5 seconds later. And B, how fast does the ball hit the ground? Right, how fast is the ball traveling when it hits the ground? Okay. The reason I use the word speed here instead of velocity, the velocity would be negative because the ball is falling and usually the positive direction points up. So since they've given us this function as a positive function, a positive increasing function, we really should use the word speed here instead of velocity. Now the velocity function, we can calculate what we're looking for here. We want the velocity of the ball at 5 seconds. I will use the V notation here for velocity. And we know that the velocity is the derivative of the position. So this is S primed of 5. Which by definition, and we could use either definition here, the h to 0 or x to a definition. We'll use the h to 0 to get practice with it. Should be the limit as h goes to 0 of s of a plus h, that's s of 5 plus h, minus s of a, that's s of 5. Put a little, my s's here. Divided by h. So we're looking for s primed of 5, which is v of 5. And I'm just plugging into that new flavor of the derivative formula. This, when we plug in the function s, is lim h to 0, 4.9 times 5 plus h squared minus 4.9 times 5 squared divided by h. Because my function s of t is this guy. So in order to evaluate this limit, I mean, if you were to just try and plug h equals 0, the big problem is an h downstairs. I cannot do that. So in order to find this limit, what we're going to have to do is FOIL out the top, combine any like terms, and see if there's something that'll let us cancel with that h down there. Let's lim h to 0. I'm going to factor out the 4.9. And then I've got my 5 plus h squared here. That's 25 plus 10h plus h squared. This 4.9 is gone. I factored it out. So I'll have minus 5 squared. That's minus 25. And all of this is still over h. The 25s eat each other up. The 4.9 can come outside the limit as a constant. And what's left is 10h plus h squared over h. Which is good news for us because both of the terms in the numerator have an h in them. So I can factor in h from the top to cancel with the h downstairs. In other words, what I get is 4.9 lim h to 0, h times 10 plus h over h, cancel, cancel, which gives me 4.9 times, now I take my limit, this is just 10 plus 0. So that's 49. And you should ask yourself, what are the units here? Well, the units of the top, this is the function s, and their outputs. So the units of the top here are meters. Downstairs, h is a difference between two inputs. The inputs for the function s are times, t, measured in seconds. So throughout this, the numerator has units meters and the denominator has units seconds. So this guy has units meters over seconds, or just meters per second. So after 5 seconds in free fall, this ball is heading down at 49 meters per second, which is pretty quick. Every second, the thing is covering 150 feet, half the speed of a paintball. Questions on the calculation here? Okay. The part B, we want.
I actually have a quick question.
Sure.
So I took calculus in high school, and so
Mm-hmm.
I know how to take like the derivative using like the shortcuts. So like on the test, would I have to go through like this form of taking derivative to get correct like full credit for it, or could I use like the faster way?
Yeah, so that's what I was saying a minute ago when we talked about the limit definitions. If the problem says use the limit definition of the derivative to do whatever, you need to use the limit definition. I cannot give credit otherwise. All right, let's take a look at the second part. We want to know how fast is the ball going when it hits the ground, right? Well, then I need to know two things. First, when does the ball hit the ground? And second, what is the velocity at that moment? So to say when the ball hits the ground, that's after falling 450 meters, which means we need to set the function that tells me how far the ball has fallen, s of t, equal to 450 meters. Which means 4.9 t squared is equal to 450. And if you divide both sides by 4.9, I'll just do the calculation here. You get about 91.84. So t squared equals 91.84. And then we'll take the positive square root of that, because my time here is definitely a positive time. We get about 9.58. Okay. Now, what I would not necessarily want to do, although you could, is run back through the calculation we just did, but using 9.58 for the value A, right? It's not a very pleasant number. And I don't want to FOIL out something that involves 9.58. I'm lazy. It would mean more calculator work. So this is where understanding the derivative as a function in its own right becomes handy. The first part of the problem, part A, was reasonable to solve using the limit definition of the derivative, kind of barehanded, just plugging in A the same way we'd do when we were finding tangent lines before. But because we've got some kind of unpleasant number that I would have to carry around through that calculation in part B, what I'm going to do instead is find v of t as a function, then plug in t equals 9.58. And there are nice ways to find the derivative v of t using some very simple tricks. But for now, we need to be practicing working with our limits. And of course, nobody else, unless you've taken calculus before, is familiar with those tricks. So v of t, if I just let the variable t stay in my definition of the derivative, this is s primed of t. Instead of plugging a specific number a in there, I just leave it. Lim h to 0, s of t plus h minus s of t all over h. And the calculation here is very much the same as what we did a second ago. This is 4.9 times t plus h squared minus 4.9 times t all over h. And since the calculation is so very similar, I am going to skip a couple steps here. This is 4.9 times the limit as h goes to 0. This would be t squared plus 2th. Oh, sorry, this is 4.9t squared here. Sorry. So this would be t squared plus 2th plus h squared minus t squared. So what we're going to have here is 2th minus h, plus h squared over h. Factoring the h, canceling with the bottom, you get 2t plus h and then sending h to 0, you get 4.9 times 2t plus 0, which is 9.8t. Check my arithmetic, yeah. So the velocity of this ball, or the speed we should really say, because the velocity would be negative because it's falling down. The speed that this ball is falling at any moment during its fall is 9.8 times the amount of time it has been falling. And in particular, at the moment it hits the ground, which is 9.58 seconds later, it will be traveling at v of 9.58 meters per second. And since v of t is 9.8t, this is 9.8 times 9.58. I'll put it down here. About 93.888 meters per second. So all of this work, what this tells us is that the velocity function, which is the derivative of the position function, is 9.8 times t. That's what we discovered over in this limit work here. And that is what it looks like. That's your derivative. But instead of a specific value from the derivative, instead of a number, it is a whole ass function. And you know what that means? It's got a graph. And we can look at the graph of this derivative together with the graph of the original function. And the last thing I want to do with you here today is something like that, but I don't want to do that with this particular function because it's kind of a boring example. I'd like to do it with a slightly more exciting function. So if you'll bear with me, we will go just a few minutes over here and do precisely that. Before I move away from this example, are there any questions about the calculation or how we got our answer at the end here?
So I'm a little confused. Like I understand you're using like that like formula you showed us earlier, where it was kind of the a plus h minus or it was f of x minus f of a, I think.
So we have two different formulas for the limit definition of the derivative. One of them involves x's and a's. The other one involves a's and h's. What I'm doing here is using the second one, but instead of an a, I am sticking with the variable t. So I'm using this version of the formula, but instead of an a here, I'm just leaving the variable inside as t. That's really all I've done. It's not something you can do so readily with this formula because there's already like one of your original variable in there, and that's kind of why they like to use the two formulas separately. But if you compare this with, let me line it up, with this, s primed of t versus f primed of a, I've changed two things. The name of the function here is s instead of the name of the function here being f. And the label I'm using for the variable or quantity inside, the input, here I've left it as the same variable we're using in the original function, as opposed to here where we call it something else. We relabel it as a with the understanding that a is a constant. What we're really saying is that here, a doesn't need to be a constant. A could be allowed to stay as a variable. And when we do that, instead of getting just a number out, we get a whole ass function out. And that's what we got here. Does that feel a little better?
Yeah, I mean, from what I understand now is that there's like various like formulas to like solve these sort of problems, and depending on which one you use, like one might be better.
Yep, there are those two different formulas for the derivative. There's the one with the h's and the one without. So the one with the h's is the one we used here. The one without, there are ways to finagle it to make it work, but this is the more natural approach for getting the derivative as a function. All right.
Thanks for explaining.
Sorry, go ahead.
I was just saying thank you for explaining.
Oh yeah, of course, of course. So before I let you go, I do want to say one or two things about the derivative as a function. We've already covered some of this material. I'm going to take just a quick peek at the textbook to make sure I'm not skipping over anything important. Yeah, so computing is boring, and that's 90% of what this is. We already talked about the definition of differentiability. We already did that. Differentiable implies continuous, failing differentiability. All right, yeah. So really the only thing to do here is that we haven't done yet is talk a little bit about graphs. So leaving the original variable as the input in the derivative, we can think of f prime as its own function. Defined by f primed of x is lim h to 0 f of x plus h minus f of x all over h. So just like we did in the last example, instead of using some specific number a here, here, and here in this formula, we just leave that input as the variable that you were using before. The domain of this new function, f primed, is going to be all of the x values where the original was differentiable, right? Because that's where this limit exists. The main thing we want to look at here is the graph of f prime of x with f of x. So in black here, I'm going to graph the function f. And the way I'm going to try to sketch a graph of its derivative, f primed, is by taking a few points and approximating the slope of the tangent line to f at those points. So here's what I'll do. Let me use blue for this. Take a point here, and here, and here, 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 and here. And we can just shade in little segments of tangent lines at each of these guys. And the trick is to remember that f primed of anything is the slope of the tangent to f at x equals a. So if this is my original function, then the derivative of my function at 0 would be the slope of the tangent line here. The derivative of my function at whatever this is, let's call this 1. Let me just mark these off. So this would, I'll call this guy 1, call this guy 2, call this guy 3, call this guy 4, call this guy 5, and call this guy 6. We can approximate the slope of each of these little tangent lines. The y value on the graph of the derivative is the slope of the original. That's what we're saying here, is that the y value on the graph of the derivative is the slope of the graph on the original. So here's the graph y equals f of x. And off to the side here, I'm going to approximate the slopes. So this guy looks to have slope like maybe 2, right? This guy has slope maybe 1. This has slope 0. This has slope like -1. This has slope 0. This has slope maybe like 1/2. It's kind of shallow. And this has slope maybe 1.5, something like that. In fact, let me go back and edit this to 1/2 because he looks to be about the same as this one. All right. So slopes on f are y values on f prime. This and this say the same thing. So if I want to sketch f prime, and I'll chop this up. 1, 2, 3, 4, 5, 6. I'll mark this as 1, 2, -1, -2. F primed of 0 is 2. That's what this says. So f primed of 0 is 2. That means the point 0, 2 is on the graph of the derivative. This little tangent slope here that I'm approximating is about 2 would mean f primed of 0 is 2. This little tangent segment with slope 1/2, he's at x value 1. So that would mean that f primed of 1 should be 1/2 or 0.5. So when x is equal to 1, the y value on the graph of f prime should be about 0.5. There's another point on the graph of my derivative. This next guy right here, where x is 2, the tangent line on the original has slope 0. So that means f primed of 2 should be 0. In other words, the point 2, 0 is on the graph of my derivative. Continuing on, when x is equal to 3, the slope of the tangent line to f is -1. So f primed of 3 is -1. In other words, 3, -1 is on the graph of my derivative. At x equals 4, the tangent line to f has slope 0. So f primed of 4 is 0. In other words, 4, 0 is on the graph of my derivative. At 5, the slope of the tangent line to the original is about 1/2 again. So 5, 1/2 on the curve. And at 6, we said 1.5. So f prime of 6 is about 1.5, which is here-ish. So a reasonable sketch of this derivative, just an approximation, might look like this. And what I'd like you to pay careful attention to are the x-intercepts of the derivative and how those relate to features on the graph of the original. Think about where the original function is increasing and where the derivative is positive. Original function increasing, 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 increasing. The derivative over those same x values is positive everywhere. The original function is decreasing, 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 decreasing. The derivative is negative everywhere there. The original function is increasing, 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 and the derivative is back to being positive there. There are a lot of deep connections that you can start to make by thinking carefully about this process. And to get a perfectly acceptable picture here does not require good estimates here, right? I was very, very sloppy about these slopes. I'm just guessing, I'm just making shit up. But as long as their relative sizes and signs are correct, you will get a good graph down here. You notice that the local max here on the original is associated with an x-intercept here on the derivative. That's a big deal. That the local min here on the original is associated with another x-intercept on the derivative. That's also a big deal. Many, many things you can start to think about once you have this picture in mind. And that's pretty much all the homework problems I gave you from 2.8 are thinking about graphs like these, matching one with the other, that sort of thing. All right, I have taken up enough of your time with this, so I will go ahead and let you go here. Does anybody have any questions they'd like to ask about how I produced the blue graph from the black graph? Okay, then before I let you go, I will just share one more thing with you. It's in your modules. I took the time to make a number of Desmos graphs to help you play with these things without having to do a bunch of drawing by hand. So if you look here, there's 3 or 4 Desmos graphs that I've put together over the years that I think help you to see what's going on. Now, obviously, this is quite busy, but you can grab the point of tangency and drag it around. So the red is the original function, and you can turn things off to declutter. Get rid of the labels if you want to declutter. But you can drag this point of tangency around and see how the red graph, which is the original, relates to the blue graph, which is the derivative. And there's several versions of these things. Here you can kind of watch the tangent line surf over the function and see how the blue graph is related to it. Again, red is the original, blue is the derivative. And this is similar, but not exactly the same, a little bit less cluttered. So I invite you to play with these Desmos graphs at your leisure, maybe before or while doing the homework. And then if you have any questions while you work through those homework sets, please come talk to me. I want to say just one more time that this skill right here, going from this graph to this graph by estimating the slopes of the tangent lines is very important. If you get good at this, you will get good at all of Calc 1. So practice this, and the stuff we're going to do next will make great sense. All right, thank you guys for sticking around. I appreciate your patience. Anything you'd like to ask or talk about before we close the meeting?
I was just wondering, like with homework extensions, we just like extend it and you approve it, or?
Yep. Yeah, go ahead and put in an extension request in WebAssign. I'll go and grant them as soon as I can. So I cleared out a bunch yesterday. I'll clear out some more as soon as we finish up here.
All right, I appreciate it.
Sure. Anything else, guys?
Thank you, John. Have a good weekend.
Of course. All right. Take care, gang. I'll see y'all on Monday.